Previously, we've been trying to fill in truth tables for our expressions in the propositional calculus. But let's look at what happens if we start with a truth table and have to get the expression. Let's go backwards. We can consider these expressions to be functions in a mathematical sense of the input variables over here. So what we're really asking is, given this truth table, what is the form of this function? In order to do this, let's look at the rows that have a t. We know that the function is going to be true when the input is this, or when the input is this, or when the input is this, or when the input is this. When p is t and q is t and r is t, or when p is t and q is f and r is f, or etc. We can connect via our OR operation the t entries in the truth table. This is because the nature of OR, right? If you have one t in a string of things ORed together, the whole quantity evaluates to true. So all that remains is for us to write out what each of these represents. P equals t, q equals t, r equals t can be represented as p and q and r. When these are all true, this quantity evaluates to true. And so in a chain of ORs with these other things, it will force the whole function to be true. If we have some f's in here, then we have to not the variables in this construction. So q equals f means I need a not q over here. R equals f means I need a not r over here. P equals f means I need a not p, and so on. So at the end of the day, what we end up with is a logic function that looks like this. It might be intimidating. There might be a lot of things here, but if we stay within ourselves, understand our ability to work with these mathematical symbols, it's not that big a deal. Because notice the OR connectives. These are all my ORs, my three ORs, and then these are the individual terms. Each one of these terms represents a row of the truth table corresponding to t. This is really important that you be able to follow this logic. So work through this, make sure you understand how to get this form out of this truth table. We have a name for this form. It's called the full disjunctive normal form. My goodness. Often in mathematics, when we deal with some sort of object, be it an algebraic structure such as a group or a matrix or whatever it is, we have different forms that object can be put into. And pretty much every domain in mathematics has something called a normal form. So in our domain, this is what the normal form looks like. This is a disjunctive normal form because it is a bunch of and terms connected with an or. Remember, we call the or disjunction and we call the and conjunction. So this is the disjunctive normal form because the main connective here are the disjunctions. It's the full disjunctive normal form because every and term contains all of the variables of the function. I just realized this should be f, p, q, and r as well. F, p, q, and r. This is a 3-variable function. Each term here represents all of the variables. That makes it a full disjunctive normal form. So remember, the two conditions to be full disjunctive is that it has and terms connected with or, and each term contains all of the variables. We can use all the equivalencies that we studied previously to take a function that is not in full disjunctive normal form and put it in full disjunctive normal form. It's really fun to say. You should just use this at dinner for the next couple days. Just slip it into casual conversation. Here's an example. Construct the full DNF. We have abbreviations, of course, for everything. Disjunctive normal form. For this logic function, a WFF can be considered a logic function here. So we start off with our basic breakdown using the implication conversion rule, and we end up with this, which then, after we distribute the s, becomes a disjunctive normal form. because I have not P and S, or not Q and S, or R and S. So we're going through these a little quicker now, right, than we did several videos ago. If you're keeping up, you should be able to see these steps. This is what we call a disjunctive normal form. But it is not the full disjunctive normal form because it doesn't satisfy the second condition. A normal, just a regular DNF is this up here, terms connected with ORs. A full DNF is going to be where we have all of the variables. So we have to add variables. How do we add variables in? Well, we use an algebraic trick. I guess it's not a trick, it's a technique, right? A technique is a trick you've used more than 3 times in math. So this is a technique. What we're going to do is we're going to AND this term, not P and S. This is missing Q. So we're going to AND it with Q or not Q. What? This is like multiplying by 1 or adding 0. Oftentimes we do this in a clever way in algebra, and then we get some great result from it. Because Q or not Q, this is true. And when I AND with true, nothing happens, right? ANDing with true doesn't change the truth value of the expression. So this is logically equivalent to this, because I can just add this term in. Normally, when we are simplifying, we look for things like this and we like them to drop out. But in this case, we are going the opposite direction. We want to have more variables in our terms. So this is what we do. If we're looking for a DNF and we have these AND terms, we can expand them by ANDing with true in a particularly clever way. Q is the variable that we need to add to this. That's one of the variables we need to add to this. And so we just do it. Then we distribute and we get these 2 new terms. So this now is equivalent to this. We have to now add R's in, right? Got to add the R. And we end up with this over here, running out of space on the previous page. Right? So we added the R's in, and now we get all of this. So now what we've done is we've taken this first term, which was not P and S, and we have fully expanded it into these 4 terms that now each contain all 4 variables of my logic function. So we're closer to the full disjunctive normal form. It's really important that you be able to follow this logic to here, because it's going to get really interesting now. Notice we have 2 more terms. We have not Q and S, and we have R and S. So we're going to have to unpack both of these in exactly the same way we unpacked this first term. This first term broke into 4 new terms. So each of these is also going to break into 4 new terms. We're going to have 12 terms here at the end of this. So hang on. Here's step 1. We're going to add a new variable back in. It doesn't matter what order you add the variables in. And then we distribute. So now we have 4 terms here. And now we have to go again, right? These don't have all 4 variables yet left. So we got to find more room on the page. And now we have to add in these extra variables. Here's the term that we had last time. Now we're adding in the AND with P or not P. We expand and get all these new terms. My goodness. Now keep in mind, don't get too scared by this. Keep in mind that this is a 4 variable function. And that is why we have so ridiculously many terms going on here in this. Here's the final result. You know what this is? This is the page that you screenshot and you show people what you're doing in your class. And they will be very, very impressed. Don't worry though, I'm not going to require of you that you run through things with 4 variables like this. This is the point at which we are very thankful we are computer scientists and we can intuit that there must be a programmatic way to do this. We can make a computer generate these forms for us if we really wanted to. But you should understand the basic logic here. You should understand how we are getting full disjunctive normal form. Why do we want it? Like, why do we want the full disjunctive normal form? Why is that a good thing? Why is that something that we would even care about? That's the case because there's certain applications of the propositional calculus that require our WFFs, require our truth functions to be in a certain form. And if we have them in this normal form, that's the form that we care about. The reason mathematical objects have normal forms is because they are, well, normal, and they can then be applied in good ways. So you can write these functions in all sorts of ways with implication arrows and all these different things. And so for some applications of this stuff, we'll talk a little bit about it in chapter 8. We want things in normal form. So it's not just a mathematical exercise just to show off, although would it be so bad if it were? Really, I mean, this is pretty cool. It actually has an end to it. There is a reason to want something in a normal form like this. Okay, again, follow through and just understand the process of expanding these things. Understand the idea that we're doing this algebraic trick that says I'm going to AND with true, and then expand from there. Use the distributive property and ANDing with true. If that was the disjunctive normal form, there is also a conjunctive normal form where the terms are going to be connected with ANDs. We're now going to have ORs that are connected with ANDs. That's the conjunctive normal form. And a full conjunctive normal form is where each term contains all of the variables. So let's work through this one. Now you'll notice, thankfully, at the beginning of this problem, that we only have 3 variables here. So this is going to be much different than the previous example. So not P or Q or R, and P or Q. So as soon as we apply the implication conversion rule, we already have something that's in conjunctive normal form. It's not full conjunctive normal form because this second term here, the P or Q term, doesn't contain all of the variables. This one does already, so we're basically almost done, except we need to introduce a new algebraic trick. We can't AND with false here, that's not going to, with true here, it's not going to work. Instead, what we're going to do is we're going to OR with false. So ANDing with true is kind of like multiplying by 1, and ORing with false is kind of like adding 0. So if I OR anything with false, it doesn't change the truth value of it. It still just defaults to whatever P or Q was. P or Q or false is the same equivalent to P or Q. So this R is the term that I want, R and not R. So I just add this term in like this, and then I use my distributive property to generate the terms. And this is it. We're done. Like there's not 8 pages for this one, right? Like we're just done. This isn't that hard a process. I just wanted to illustrate a more complicated one on the previous example. So there you go. This is the end of this material. So make sure that you understand these truth functions, be able to generate the truth function from the truth table, and be conversant in the normal forms.